All right. Hello, everyone, and welcome to the webinar. My name is Rawley Loken. I'm a senior managing consultant at Energy and Environmental Economics, or E3. Today, we're going to be discussing the results of a new report we produced for the Center for Applied Environmental Law and Policy, or CAELP. The topic of this report is decarbonizing industrial heat, and we'll discuss how we compiled a database of facility level heat demand, examine the cost effectiveness of various decarbonization technologies, and then finally looked at the impacts of a couple different policy mechanisms on the cost effectiveness results. So at this point, I'll hand it over to Grace Van Horn from CAELP to say a few words about their motivation for commissioning this work.
Thanks, Rawley, and thank you so much to the entire E3 team for all of their work on this detailed and really fascinating analysis. I'm sure many, if not all of you on this webinar today are familiar with the general contours of the economics around industrial heat decarbonization, importance of gas versus electricity prices, relative efficiencies of boilers compared to heat pumps, all of those things. But what we really wanted to do with E3 for this project is to deep dive into those issues using the best possible unit by unit data of existing industrial boilers that we could access and develop. And ultimately, using that data set, we had three key questions that we hoped to explore. First is how much natural gas-fired industrial heat could be cost-effectively replaced with lower emitting options? Second, what were the key economic drivers for those units that were and were not cost-effective, or those that may be on the margin, utilizing that unit-specific and state-level data? And three, how could targeted policy interventions help improve the economic case for industrial heat decarbonization? And so we're really excited to share these results with you today and to release both the report, which has really excellent insights, as well as the economic model that E3 developed to create the report. And we really hope that this will allow stakeholders such as those on this webinar to really dig into the data and explore both the underlying economics and possible solutions in thinking about policy interventions. So again, big thanks to the E3 team, and I'll pass it back to you all to dig in.
Thanks. You can go to the next slide, Sean. I'll give a really quick introduction to E3 for those of you who don't know us. We're an energy consulting firm with over 130 full-time consultants in 5 cities across the US and Canada. We work for a really wide range of sector for clients across the energy sector. So investors and developers to utilities and a lot of public agencies and nonprofits like CAELP. Some of the recent work we've done that's particularly relevant to this analysis is looking at industrial decarbonization as part of our economy-wide analyses for the US Climate Alliance, working on an industrial carbon neutrality plan for a North American auto parts manufacturer, and also supporting multiple utilities and state agencies to develop clean heat plans and electrification strategies. And on the next slide, I'll just walk through the agenda. So once we finish this brief introduction, I'll hand it over to my colleague, Sean Smillie, who is the project manager for this analysis. He'll go through the report findings and give more detail on the background, how we characterized industrial heat, and then the cost effectiveness results. We'll have 10 minutes at the end for audience questions and answers. And so you'll see on WebEx, whether you're in the browser or on the application itself, there's a Q&A button. If you click on that, that's where you can submit questions. We'll try to take all the questions at the end during that session, but feel free to submit questions during the presentation as they come up, and we'll try to get to them in that time. Then we'll have a final wrap up and adjourn by 3 o'clock Eastern. The links to the final report and the model that was actually used for this analysis are all going to be available after the webinar, so we'll send out links for that as well. And just to note that this webinar will be recorded for viewing later. So with that, I'll hand it over to Sean.
Thank you, Rawley. So diving right in, as many of you I'm sure are aware, natural gas is the largest energy source in the industrial sector. provides about half of industrial energy and is the most widely used heating fuel in manufacturing. To decarbonize the economy, all sectors are going to need to reduce their emissions, and there's still a lot of work to do in all of these sectors. But many of the other sectors have achieved either progress in reducing some of their historical emissions or have fairly comprehensive policy frameworks to achieve some of those reductions. The industrial sector accounts for about a quarter of the US emissions, and they've historically been flat over the past few decades. The diversity of the industrial sector does make it a little bit more difficult to analyze the potential reductions and develop more comprehensive policy frameworks. And part of the challenge is the low cost of natural gas, because it makes the economics of replacing it with lower carbon emitting options higher by comparison. So ultimately, a more comprehensive policy framework will be required in the industrial sector to reduce industrial emissions along the lines of the targets of many states and federal agencies. And part of this may very well include addressing some of the cost differences. We focus on indirect heat in manufacturing. So that's indirect heat is heat from boilers and combined heat and power facilities, also known as cogeneration. And we look at the cost effectiveness of replacing these gas technologies with lower carbon or decarbonized replacement technologies. We are explicitly excluding process heat or direct heat from this analysis, which is provided by a much more diverse set of technologies. And that requires much more application-specific evaluation of the current costs and technical requirements for all those technologies. But by contrast, the indirect heating equipment is a lot more standardized. And that allows for a much more standardized evaluation of some of these replacement costs. Boilers and cogeneration technologies consume about 2,100 teraBTUs of gas annually. That's about 30% of manufacturing and 20% of total industrial gas demand. Combusting that gas corresponds to 110 million metric tons of annual CO2, or about 18% of manufacturing GHGs. So in looking at the indirect heat from manufacturing, we built a facility level database. This database combines existing gas heating unit data from EPA's GHGRP dataset with detailed manufacturing subsector estimates of temperature requirements for the Department of Energy and NREL sources. Combining those two data sets gives us data on about 500 industrial facilities with over 900 different combustion units, providing heat to about 3,500 different temperature streams. We also use energy prices and electricity emission trajectories from the Energy Information Administration's annual energy outlook, and these vary by state within the model. So putting all these together, the combined database lets us examine the cost effectiveness of replacing indirect heat with decarbonized options, considering a wide range of facilities from different subsectors with a wide range of capacity factors, energy consumption, energy prices, and temperature requirements. A brief look at what that database contains. On the left, you can see the wide variety of temperature requirements, both across and within industrial subsectors. Notable here, I think, is that we're estimating that about half of indirect heating gas consumption is for temperatures below 100 degrees Celsius, and 80% is below 200 degrees Celsius. That lower temperature heat is important because heat pumps are much more efficient at providing heat at lower temperatures. So the lower the temperature, the more economically feasible heat pumps specifically could be. Most gas use under 200 degrees Celsius is from the food and beverage, chemical, and paper subsectors. And most of the indirect heat above 200 degrees C is from the chemical and refining subsectors. Jumping into some of our key results, we use a levelized cost of heat to assess the costs of current and potential replacement technologies. The levelized cost of heat is calculated very similarly to the levelized cost of electricity, or LCOE, which is a metric that you might be familiar with in characterizing renewable cost, wind and solar costs. And the levelized cost of heat is a forward-looking assessment of the capital, operating maintenance, and fuel costs of the technology, levelized across heat produced over the investment time period and discounted to the present. So we're looking at the cost of switching from gas technologies to decarbonized technologies, including heat pumps, electric resistance with and without thermal energy storage, renewable natural gas, and hydrogen. On this chart, we're comparing to the cost of boilers. We're on the far right. Existing natural gas boiler represents the cost of operating boilers that have already been installed. And new natural gas boiler just to the left represents the cost, including the cost of replacing that boiler because the old one was at the end of its life. So the difference there is essentially capital costs. The range of the box and whiskers represents the variation in results across the 3,500 facility and temperature combinations that I discussed previously. And what we're finding is that heat pumps are cost competitive with boilers at some facilities below 100 degrees C, especially when that boiler already needed replacement. Otherwise, the other decarbonized technologies are generally much more expensive than natural gas, especially at higher temperatures. In the rest of the presentation, we'll be exploring all of these technologies in a little bit more detail, but we do have a greater focus on heat pumps as the technology that's closest to cost competitiveness. So here we're looking at the cost structure of the heat pumps relative to a boiler and seeing that the majority of costs are fuel rather than operations and maintenance or capital costs. When we refer to fuel, what we mean is natural gas for boilers and electricity for heat pumps. Like we've said already, one advantage of our database is that we're using this real facility self-reported data, particularly for, which is particularly useful in looking at the capacity factors of the existing combustion equipment. The average capacity factor that we're finding for these 900 combustion units is 32% when capacity weighted. That translates to about 54 hours a week if operating at full capacity. And that is lower than has been assumed in some of the previous assessments of some of these decarbonized technologies on prototype facilities or based on typical facilities. And that does increase the costs of some of these technologies because lower capacity factors mean that capital cost can be spread out over fewer units of delivered heat. That being said, capital costs are still a minority of the levelized costs that we're showing here, which does have some implications that we'll come back to towards the end of the presentation. So here we're assessing how much natural gas demand can be cost competitively replaced with heat pumps in 4 different cases. We're defining the cost competitiveness as when the levelized cost of a heat pump is lower than the levelized cost of gas equipment, whether that's a CHP equipment or a boiler, at the facility and the temperature level. On the left, we're showing a comparison to an assumption for gas equipment that it needs to be replaced because it's at the end of its life. On the right, we're showing a comparison to when that gas equipment is existing and does not need to be replaced. We also assess 2 different natural gas prices, both from the EIA's annual energy outlook. The reference case is from the EIA's reference case, and the higher gas price sensitivity is from the scenario that has the highest natural gas prices. We're showing results here for 15 states that have high natural gas consumption in indirect manufacturing heat, a variety of electricity and gas prices, and diversity in industrial subsector and geography. We found that without policy support, about 1 to 5% of gas demand could be cost competitive to replace if the gas equipment is not at the end of its life on the right. And that increases to 7 to 28% on the left if the gas equipment does need to be replaced. Since this equipment is long-lived, most of it operates for several decades, turnover at the gas equipment end of life would take several decades. So that is the major consideration when comparing the left and right of the chart. In addition to some of the factors that I'm showing on the slide, we also found that some of the major drivers of cost competitiveness are lower required temperatures because the heat pumps are more efficient at lower temperatures, as well as capacity factors of the facility. Higher facility capacity factors correlated to higher likelihood of the heat pumps being cost competitive. We also look at thermal energy storage paired with electric resistance heat. Thermal energy storage allows a facility to capture lower electricity prices while wind and solar are abundant and store that thermal energy for when it's needed. So we found that resistive heat with thermal energy storage can be competitive with existing gas if the equipment output capacity factors are high. So you can see here the change from the levelized cost of heat on the blue line at the weighted average capacity factor of 32% lowers a significant amount when you assume a capacity factor of 90% on the yellow line. It's also more cost competitive when electricity prices are very low. So as you move to the left side of the plot, and that likely requires access to low cost and abundant wind and solar resources, including some amount of generation that might otherwise be curtailed. That really is how we anticipate these facilities being able to get to achieve the electricity costs at the low levels needed, lower than the installed cost of wind and solar to make this cost competitive. We also evaluate sensitivities for RNG and hydrogen costs. So in the modeling, we use assumptions for RNG prices that reflect a variety of feedstocks, and that impacts RNG pricing because of how their environmental attributes are sold into credit markets, like the federal renewable fuel standard and California's low carbon fuel standard. So for clarity, the prices that we're using here are prices and not production costs for RNG. For hydrogen, we're using pricing from the DOE that assumes that the full 45V tax credit is available. And we have 3 pricing sensitivities that reflect the differences in hydrogen storage and transportation infrastructure availability. In general, we find that electric heat is more cost effective than decarbonized fuels for the majority of cases, but there are there is a few important exceptions. But before getting into the exceptions, just want to reiterate some of the higher level points. At lower temperatures, heat pumps are most cost competitive regardless of assumptions or sensitivities around RNG and hydrogen costs. At high temperatures, there exists a substantial cost gap between natural gas and all the decarbonized options. Looking more specifically at RNG, landfill and wastewater RNG can be cost competitive with electric options at higher temperatures in regions that have less favorable electricity prices. And at higher temperatures, hydrogen can be lower cost than the electric options where there's cheap storage and transport available. Essentially where there's access to hydrogen pipeline and the geology is favorable for underground hydrogen storage. So next we look at the change in emissions from adopting some of these low carbon technologies. So we're assessing how both CO2 and NOx emissions would change, and we're including for the electric technologies, emissions from upstream electricity generation. What we're finding is that heat pumps will always reduce CO2 emissions compared to gas boilers, even accounting for those upstream electric generation emissions. And that's largely due to the higher efficiency of the heat pumps. For the most part, the same thing is true for electric resistance, except in a very small amount of cases with higher emitting electric grids, where those upstream electric emissions might actually exceed the gas boiler emissions. That is for a pretty small percentage of cases. For NOx, we see even larger emission reductions with the electric technologies. And that's in part due to the presence of emission control technologies on the fossil fuel generation technologies on the electric grid, as well as some of that electricity being provided by renewables. We next calculated the marginal abatement cost of replacing gas boilers with heat pumps. The marginal abatement cost is the cost of reducing CO2 emissions per ton of emission reduction. What we're finding is that while only 1 to 28% of the gas demand was cost competitive which I reported on a previous slide, without explicitly valuing the emission reductions. When you compare these costs to the EPA's to social costs of carbon that have been used by the EPA in recent rulemakings, about 44 to 80% of the under 200 degree C indirect heat can be abated for costs lower than $98 per ton, which was used in a 2024 rulemaking. And 66 to 75% of gas demand could be reduced for costs under $190 per ton, which was determined through a EPA working group. So this does indicate that additional policy action to increase the adoption of lower emitting technologies could lower overall societal costs after accounting for the climate damages of emissions. So evaluating a few different policies here to increase the cost effectiveness of heat pumps more specifically, we chose these 4 policies because our modeling framework is appropriate to evaluate the potential improved cost effectiveness that they could drive. We certainly don't claim that these are the only policies that should or could be considered. Starting from the left, we looked at an investment tax credit, which is available in the first year as a percentage of the heat pump capital cost. We also look at low-cost financing, where the capital cost can be financed at a lower rate than the investment discount rate. And those 2 policies are really focused on reducing the effective capital cost in the investment calculation. Next is the carbon price. So that improves the relative economics of the low carbon alternative by pricing emissions from gas consumption, as well as upstream electric emissions for the electric technologies. And then lastly, there's the production tax credit, which we model as an annual tax credit for 10 years for each unit of heat produced, so dollars per MMBTU. And the nominal value of that tax credit does get scaled down, where the percent reduction in emissions considering the electric grid does not meet certain percentage thresholds. In all cases, we are comparing the heat pump cost effectiveness to existing gas equipment, assuming that the adoption goal for the policy would not be limited to replacing gas equipment at the end of the gas equipment lifetime. This is a more conservative assumption and does lead to lower rates of cost effectiveness. So we modeled the 4 policies at a few different levels as are labeled on the chart here. We modeled all 4 of them separately and certainly do realize that in reality, combinations of these are possible. And while the results differ depending on the level chosen, what we do see pretty clearly is that policies that are focused on reducing the investment costs, so the ITC and low-cost financing, have lower ability to drive significant adoption than policies focused on improving the relative operating costs. So the ITC and the low-cost financing really only increase cost competitiveness by 1% or 2%, whereas the carbon price and PTC at the levels that we model could increase adoption 20-fold. Because of the differences in findings here, in the webinar here, we're just going to dig into results further for the carbon price and PTC, but I do encourage you to look at the report for more information on the investment tax credit and low-cost financing. So these are results for the production tax credit. On the left, there's a more detailed breakdown of at the different PTC levels, the nominal levels, how much cost competitive heat pump, how much gas demand could be replaced by heat pumps cost competitively. So we estimate that for a PTC of $2.50 per MMBTU, the amount of gas demand that can be electrified increases to 3% at a tax expenditure of $67 million. Whereas at the top level we evaluate of $10 per MMBTU, that would make 24% of gas demand cost competitive to electrify at a tax expenditure of $1.7 billion per year. On the right, the amount of gas consumption that can be reduced at net abatement costs less than that $98 per ton that we mentioned on a previous slide increases from about 80 megatons to 180 megatons for that $10 per MMBTU tax credit. This is showing the levelized cost of heat for low carbon technologies net of the PTC set to $10 MMBTU, which again is the highest value that we modeled. It's showing how heat pumps and electric resistance with thermal energy storage in particular become much more cost competitive with gas boilers. We do want to note that at some of these high PTC values, there is potential for heat to be produced at a profit regardless of whether it gets used in a manufacturing process. So we do want to highlight that it would be valuable for there to be further study on the design and level that's appropriate to drive substantial adoption of some of these technologies without over-subsidizing the cheapest use cases. One of the proposals that's been put forward for this is to vary the tax credit depending on the temperature output, but a full evaluation of this as well as other options that are available is beyond the scope of what we did here. Moving on to some additional results on the carbon price. The results do break down fairly similarly to some of the PTC results at the levels that we are modeling. So a carbon price increases the gas demand that can be cost competitively replaced from 1% up to 5% at a carbon price of $50 per ton. And that goes up to 30% at a carbon price of $150 per ton. So that 30% value is 6% higher than calculated for the highest value of the PTC that we assessed. And the difference largely derives from the differences in the policy structure that we modeled. So namely, how with the carbon price, upstream electric emissions are also subject to the carbon price. Whereas with the PTC, the nominal PTC value is derated where the percentage reduction in emissions, considering those upstream electric emissions, doesn't meet an emission reduction threshold. On the right, the amount of gas consumption, we're showing how the amount of gas consumption that can be reduced at net abatement costs less than that $98 a ton increases from 80 megatons up to 215 megatons. So to wrap up, decarbonizing industrial indirect heat is an important component of economy-wide decarbonization. Without policy support, heat pumps can cost competitively replace 1 to 5% of existing gas equipment, providing indirect heat in manufacturing, particularly at low temperatures, high capacity factors, and low electricity prices. However, substantial progress can be made within the EPA estimates of the social cost of carbon. Of the 4 policies that we analyzed, a production tax credit and a carbon tax are most suited to drive meaningful adoption of heat pumps. And further work is needed on the policy design aspect to ensure effective implementation. But these policies we do think are promising, given that they have the potential to lead to up to 30% of gas demand and the emissions associated with them being cost effectively replaced at the policy levels that we evaluated. So with that, concludes the formal presentation, and we'd love to take any questions.
Thanks, Sean. So I've been keeping track of some of the questions that have been submitted throughout the presentation, and so start answering those here. The first one is about the projections for electricity prices and emissions factors that were used for this analysis. I know you said previously that those came from Annual Energy Outlook, but I'm wondering if you could give a little bit more description kind of what the price and emissions trajectory looks like for electricity.
Sure. So yeah, these do come from EIA's Annual Energy Outlook. They do vary over time as well as between regions of the country. But on average, the gas price comes out to about $4.50 per MMBTU delivered cost to the industrial facility in our reference case, and $6.75 in the high gas case. And those are in real dollars, not nominal dollars. The electricity prices also vary over time and by state, but they average about 6.5 cents per kilowatt hour nationally and over time, which for comparison to the gas prices comes out to about $19 per MMBTU.
Great, thanks. And the next one is another technical question about how we modeled the performance of heat pumps. So I was wondering if you could talk about how we calculated the efficiency gains of heat pumps and whether that was specific to certain processes or industries, or if it was just kind of based on the temperature range of the application.
So this was based on our database of temperatures. So we modeled based on the actual variety of temperatures, not just the 3 temperature categories that we included in the result summary. And we model it as 50% of the theoretical maximum efficiency that can be achieved by a heat pump between two different temperatures. And that follows some of the work that's been done showing that that is around where most industrial heat pumps are delivering today. And we also used 20 degrees Celsius as the source temperature for the heat pump, which is fairly consistent with some of the assumptions that have been used in other studies on this question.
Great. And I think one more about the technical characteristics for the heat pumps. How did we model the capital cost for this analysis?
Sure. So we have the capital cost decline at higher installation capacities. But in terms of the average for the installed units, it was about $410 per kilowatt hour. which is more expensive than our assumptions for gas boiler costs and electric resistance boiler costs as well.
Great. See, one other question is if CHP units, if you could speak to some of the results for CHP units, given that they were not included in the box plot graphs as counterfactuals.
Sure. So I definitely encourage you to go look at the report where there's some more detailed results on the CHP units. Modeling of the CHP replacement is a little bit more complicated because they're not only providing this heat, but they're also generating electricity. Because there would be no emission benefit from replacing the heat production without decreasing the fuel combustion for electricity generation as well. From an economic standpoint, we modeled CHP replacement to require that the facility either purchases electricity from the grid to counteract any reduced emission electricity generation, which does increase the relative cost for CHP. That makes the cost comparison on some of those highlight slides a little bit harder to compare to. So we do report differences in relative costs in the report, and you can see that in a few of the figures in the written report.
Great. And we got some questions around the financial assumptions that went into the levelized cost of heat metric. So I was wondering in particular, the 10% real discount rate, if we can speak to how that was set, and then if that's something that can be adjusted in the model that's going to be posted later.
Sure. So we realize that that discount rate might vary by firm and it might vary by industrial subsector. So that is very much one of the inputs that can be easily changed in the publicly available model. So we would encourage you to, if you're interested in that question, to go look at the publicly available model and use the assumptions that you think are most appropriate for the use case that you're interested in.
Great. And we got another one on the production tax credit and kind of, how to design that. And the question is if it could incentivize low energy efficiency processes. So I'm wondering if, since that's more of a policy one, if Grace, you wanted to respond to that.
Sure. Yeah, for this, I would want to highlight specifically something that Sean said, that there are clearly a lot of different policy design considerations here when thinking about any of these four options. I think your question is getting a little bit maybe at, could there be perverse incentives or outcomes based on how a PTC is designed? Certainly that's a possibility, but at least in the way that we have structured this within the model, a firm or a facility is able to access a greater PTC if they achieve greater emissions reductions from their baseline, which is to say that the more emissions that are reduced, the more PTC is achieved. So, but again, similar to what Sean was saying around the firm level discount rate, this is something that can be modified within the model for anyone who would like to explore kind of the different impacts of different PTC designs.
Great. And another question about the emissions reductions from electrification relative to the counterfactual natural gas equipment. The emissions reductions that you showed, are those over the whole time period? And what would be the case if electricity emissions, if the emissions intensity of electricity does not reduce as fast as was assumed for this analysis?
So the charts that we showed on emission reductions, those are incorporating a 20-year investment time frame. And over those 20 years, we did assume, based on some of the AEO technology cases, an emission decline for electricity of 70%. And that does correspond roughly to the EPA's modeling for the latest electric generator regulations as well, which is why we used that emission reduction scenario. So we, if those emission reductions are not achieved, we would still see significant emission reductions from the heat pumps in particular. So even in the first year of the analysis, with essentially the current grid emission rates, heat pumps would achieve a 50% emission reduction on average.
Great, thanks. And a question kind of around the characterization of industrial heat. In the database, does it seem like a lot of the energy use and emissions are concentrated kind of at a few really large facilities? And so would it be kind of advantageous to design policies that just target kind of the biggest emitters? Or did it seem, more spread out across facility size?
Yeah, that's a really good question, and something that we had talked about internally a fair amount as well. So the emissions from industrial heat do come from a lot of different facilities. So while there are some really large facilities that operate at very high capacity factors, in the grand scheme of things, even if you get most of them, it ends up being a meaningful but small percentage of overall industrial gas demand. So for example, the GHGRP database that we use to pull some of the facility level data from itself it would be considered some of the higher emitting industrial facilities in the US based on the reporting threshold for that data set, but it only accounts for about half of the natural gas demand. So even if you get all 500 of those facilities, you only get about half of the gas demand for indirect heat manufacturing. So we do think that that a industrial decarbonization policy should probably account for a broader range of facilities than just the largest facilities to really achieve a higher impact there.
Great. And another question we got on policies is what other policies we would be interested in pursuing that promote electrification, especially as it regards to the electricity to fuel price ratio? Because as you were saying earlier, Sean, we see that the fuel cost is really kind of the biggest driver of the overall levelized cost of heat here. But I'm wondering, since that's a policy one, if Grace, you wanted to take this one.
Sure. Well, I guess one thing that I would really highlight here is that the policies that we selected for analyzing in this report are really those that are focused most on that issue, on the electricity fuel price switch, and those that are really driven mostly by the economics of switching between a natural gas boiler and one of these alternatives. Obviously, when thinking about electrification more broadly, this cost effectiveness is certainly one of the key barriers, but it's not the only one. So there are other things such as thinking about utility engagement and interconnection barriers, thinking about technical assistance and training for folks who would be maintaining these. So there are a lot of other considerations when firms are thinking about making this switch that I think could be addressed through policy, as well as some of the more economic options that we looked at today.
Great, thanks. One other technical question was just about potential other sources of hydrogen, and I think, Sean, am I correct that the only thing that was included in terms of hydrogen sources here was green hydrogen for both the emissions intensity and price, but that the model will have the ability for users to test other assumptions around sources of hydrogen.
Yeah, that's right. So the cost data that we use comes from estimates for green hydrogen. But really, what the model is doing is taking inputs on hydrogen prices and flowing that through. So if there are other prices that you'd like to use, that can be done in the model.
Great. So I think with that, we want to move over to, I think there's a final wrap-up slide, and we have further information for where people can get the information for this report. Awesome. So as we noted at the beginning of the webinar, the final report and the model are going to be published on the E3 website, and we'll send out a link to all the participants of this webinar to take a look. You can download the model, you can play around with the policy parameters and look at the impact on the results. The screenshot on the right here is just an example of some of the universal inputs and policy design inputs that were used for this analysis. And please feel free to reach out to E3 if you have any questions about the model inputs or the analysis. And I'll leave it if Sean or Grace, if you have any other final words you'd like to part with.
Thank you very much for attending.
Thank you.
Thanks, everyone.